Now we finally come to the Arzelà Ascoli theorem, and to state this theorem we will use the following terminology. So again, our standing assumption is X is a locally compact Hausdorff space and Y a metric space. So with this assumption, a subset f of the space of continuous functions from X to Y is said to be pointwise relatively compact. Pointwise relatively compact if for each a in X we have that the sets f of a that we defined in theorem 2.2. So f of a was just the set of evaluations of all functions in f at the point a. If this set fa has compact closure in Y. So we have already used this kind of condition in theorem 2.2, and here we used the notation CA for the closure of FA in Y. So we are assuming that for each A, this set CA, which is the closure of FA, is compact. And if this happens, then we say that this subset F is pointwise relatively compact. So which means that for each point A, when you take the evaluations, this is the pointwise part of pointwise relatively compact, and relatively compact simply means that the closure is compact. Okay, so this is why it is pointwise relatively compact. Okay, so with this definition we can state the theorem of the Arzelà Ascoli theorem. So theorem 4.1, and this is the Arzelà Ascoli theorem. So we have already seen one part, the forward implication of the Arzelà Ascoli theorem, which is that if X is a topological space, not necessarily locally compact Hausdorff, X is a topological space and Y a metric space, then if a subset f of Cxy is equicontinuous and pointwise relatively compact, then the closure of f in the topology of compact convergence. So this is the closure of f in Cxy in the topology of compact convergence then this is compact, okay, as a subset of Cxy. Here notice that I'm using the terminology pointwise relatively compact is exactly, this means that there's this FA closure, which is the closure of all these evaluations of functions f in f at the point A. This is compact in Y. So I assumed here X in the terminology, I assumed X locally compact Hausdorff, but of course this terminology does not depend on the topology on X. It only depends on the space of continuous functions and the topology on Y, which is the metric topology. And so in fact this also works for any general topological space X. So with the same definition we have that F as a subset of Cxy is equicontinuous and pointwise relatively compact, then the closure of f in the topology of compact convergence in CXY is compact. Okay, so this we already proved, and this was theorem 2.2, which is already done. And secondly, converse of 1 holds if X is locally compact and Hausdorff. So here is where we need the locally compact Hausdorff property, and this Arzelà Ascoli theorem. So the Arzelà Ascoli theorem gives a characterization of compact subsets of CXY in the topology of compact convergence. Right, so this is an equivalent condition provided, of course, that X is locally compact Hausdorff. So okay, so we have already seen the first part, the proof of the first part, and we need to show the proof for the second part. So let's see why the converse holds if X is locally compact and Hausdorff. So we begin with our assumption for the second part. So we have chosen a subset F of CXY such that the closure of F in the topology of compact convergence, so CC, is compact in CXY. So we have assumed this, and we need to show two things to show that. First of all, that for each A, so for each A in X, the closure of FA in Y is compact. So this is the pointwise relatively compact part, relatively compact. And the second part is that F itself is equicontinuous. Okay, so let's try to show both. So as a notation, let me denote this closure of F in the topology of compact convergence by this H. So to prove one, to show one, note that H is compact in the topology of compact convergence in CXY. And now we consider the following map. So this map is from CXY to X Cartesian product CXY, and then we take the evaluation function that we have defined in the last lecture, and we end up in Y. So it is composed of, it's a composition of two functions. So for this J will depend on a point at X. So let me write it as JA, and this will be a composition of two continuous functions. When X is a locally compact Hausdorff space, we have seen that the second one, the evaluation map, is continuous, and the first one will automatically be continuous, and so we will have a continuous map. And the point is that if H is here and you map it to Y, so this is some HA, say, since this is a compact image of a continuous image of a compact set, then this is compact. So and if a closure will lie inside HA, and therefore FA closure will be compact also. So let me try to write down these things, what I mean by JA, first of all the JA map. So JA is a map from CXY to X cross CXY, and this map is nothing but taking F and mapping it to the point A comma F in this Cartesian product. And this is continuous because the first coordinate function is continuous, and also the second coordinate function is the identity. Well, the first one is constant, is just the constant map, and the second one is the identity map. So in fact JA is nothing but the product of the constant function. So let me write lambda A cross the identity map. So where lambda A is a map from CXY to X, which takes lambda AF to A. Okay, this is a constant map, and we have seen that constant maps are continuous, and the identity map is simply the map from CXY to CXY, which takes identity of F is equal to F. So JA is the product of two continuous functions, and therefore this is a continuous function. So JA is continuous. And we have also seen that the evaluation map is continuous since X is locally compact Hausdorff. So we have seen this in the last lecture, and therefore the composition, so let me write it as H, which is the composition EV composed with JA, and this is a map from CXY to Y, okay, which takes basically the any function F to the point F of A, right? So this is a kind of an evaluation function, but now defined directly on CXY rather than X cross CXY. So this is also a kind of evaluation function. So maybe I can write it as evaluation rather than H, we can write it as evaluation at A. So this is a continuous function, is continuous. And now this means that the image of the set AH under evaluation A is nothing but the set HA, which is the set of evaluations HA for all H in H. So this is a compact set, compact subset of Y. And now I claim that the closure of FA belongs to HA. So why is the closure closure of FA is a subset of HA. So why is the closure a subset of HA? So remember that H was the closure of F in the topology of compact convergence evaluated at A. And here you have first the evaluation and then the closure. Okay, so this is because f of F first of all lies inside H. So this means that the evaluation map applied to F is a subset of the evaluation map applied to H. This is nothing but H of A. On the other hand, the left hand side is F of A. So this means that F of A is a subset of HA, and this is closed because it is compact, as it is compact. Then this means that FA closure is a subset of HA. So therefore we have that the closure of FA lies inside a compact set. This means that FA closure is compact for each A in X. So this means that F is pointwise relatively compact. So the only thing that we need to show now is the second one. Let me go back. So we have shown the first part, which is that F a closure is compact, and now we have to show that F is equicontinuous. So why is F equicontinuous? So this needs some results that we have proved earlier. So to show that F is equicontinuous, so we will show that the collection H, which is the closure of F in the topology of compact convergence, is equicontinuous, and subsets of equicontinuous sets are equicontinuous, so F should be equicontinuous as well. And so let us show now that H itself is equicontinuous. So to show that H is equicontinuous, we will show that given any A in X, we will show that H is equicontinuous at A. Okay, and since equicontinuous means that it is equicontinuous at every point, so it is sufficient to take an arbitrary point and prove that H is equicontinuous at that point. So to show that H is equicontinuous at A, it suffices to show that for a compact neighborhood, or rather a compact for a neighborhood U, U of A such that U closure is compact, the following collection, which I denote by G, which is the restriction of all functions in H. So let me write H, small h. So H in H. So this is equicontinuous at A. Because if we find a neighborhood of A which is smaller than U or U closure, then we will have a neighborhood in the ambient space as well. So it suffices to show that this restriction collection is equicontinuous. So G is a subset of the space of continuous functions from this set A to Y, where A is nothing but the closure of U. Okay, so this is a compact set by our choice of U, and we will show that the following function R, which is from Cxy to Cay, which takes a function f and takes the restriction of f to A, this is continuous when both Cxy and Cay have the topology of compact convergence. Okay, so with this with this topology on both on Cxy and Cay, R is continuous. So why does that help? So let's first see why this will help us. So then this implies that G, which is nothing but R of H, is compact, and so this is compact in the topology of compact convergence, because H is compact in the topology of compact convergence and R is continuous, so G is compact. On the other hand, G is a subset of Cay, and on compact sets the topology of compact convergence is the same as the uniform topology on CAY. Okay, this we have shown before, that the topology of compact convergence and the uniform topology become the same when the domain function, when the domain of the function space of functions is compact. So this means that G is compact in the uniform topology now. On the other hand, the uniform topology is a metric space. So with the uniform topology, CAY is a metric space. So the uniform topology, as we have seen, is defined by a metric. So compactness in a metric space is equivalent to G being complete and totally bounded. So this was one of our characterizations of compactness in metric spaces. So metric space is compact if and only if it is complete and totally bounded. We don't really need the completeness, but we will definitely use the totally bounded. So G is totally bounded in the uniform metric. But we have shown in one of our lectures in the previous week that this means that totally bounded implies that G is equicontinuous. So we have shown this before, that totally bounded subspaces of metric spaces, totally bounded in the uniform metric implies that G is equicontinuous with respect to the metric D on Y. Okay, so therefore G is equicontinuous, and let's go back where we were. So G is equicontinuous means that H is equicontinuous, and this is what we wanted to show, except that we did not yet show that this restriction function is continuous, and so let us try to show this, and that will complete our proof of the Arzelà Ascoli theorem. So let's try to show that, R from CXY to CAY is continuous when both are given the topology of compact convergence. Okay, so it suffices to show that given any f in CXY and a basis in the topology of compact convergence, so let me call this basis B in the topology of compact convergence in CAY. So say B is of the form B, C, F restricted to A, Y, where C is compact in A. So then it suffices to show that there exists a basis element which we call B prime, which will be just the basis element. So sorry, this is epsilon. So the basis element in CXY such that R of B prime is a subset of B. So why can we take the set BCF comma epsilon? Because C is compact in X, since C is compact in A and A is compact in X. Okay, so if C is compact in A and A is a subspace, compact subspace of X, then C is compact in X as well. But now, since C is a subset of A, if we have some RG belongs to R of B prime, where G belongs to B prime, which was nothing but BCF epsilon. So this means that the supremum over C, X in C, the distance between Fx and Gx is less than epsilon, and this means that the supremum over X in C, D of F restricted to A, X, G of G restricted to A, X is also less than epsilon. So here I am using that C is a subset of A, and this is nothing but this means that G restricted to A belongs to BC F restricted to A epsilon, and this proves that R is continuous, and this completes the proof of the second part of the Arzelà Ascoli theorem, and we have already proved this first part before, so it completes the whole proof of the Arzelà Ascoli theorem. And just to finish off, here is a nice application of the Arzelà Ascoli theorem. So here is the theorem. It says that if X is a compact Hausdorff space, Fn is a sequence of continuous functions, so from X to Y, such that the set F, which is basically formed by the sequence Fn, is equicontinuous, and further on that if F is a function not necessarily continuous, such that Fn converges to F in the topology of pointwise convergence. So Fn converges to F pointwise, then F is continuous and there exists a uniformly convergent subsequence of Fn converging to F. So in general we know that if you have a sequence of functions converging pointwise, there may not be any uniformly convergent sequence, but if the set is equicontinuous, if this F is equicontinuous, then we have a uniformly convergent subsequence, and this automatically implies 2 implies 1 by the uniform limit theorem, because we have a sequence of continuous functions converging uniformly to this function F. So this of course uses the fact that, so let me just write what are the facts you will need, and I'll put this as an exercise, so proof as exercise, and you will need first of all that the uniform topology and topology of compact convergence coincide on Cxy because X is compact, and secondly Fn converges to F pointwise implies that this set F, which is nothing but the set of functions Fn for n in n, this is pointwise relatively compact. Pointwise relatively compact, and for this you can prove the following. So for A in X, prove that Fa closure is nothing but the set Fna n in n union F of A, and we know that Fna converges to F of A, and therefore this set is compact. Okay, so you just have to show this closure is given by this union, and therefore you have that F is equicontinuous and pointwise relatively compact, which means that F is compact in the topology of compact convergence, but then now you can use the fact that uniform topology and compact convergence coincide and prove that there exists a subsequence by using the sequence lemma. Okay, so because now you have a metric space, so you can form a sequence that converges to a limit point. Okay, so there are a lot of steps involved, and if you have any questions, please ask me on the discussion forum and I'll be happy to help. And with this I come to the end of our course, and in fact well, first the end of the discussion of the Arzelà Ascoli theorem and also the end of the course. So if you have any questions until the exam date, you can ask me on the discussion forum and I'll be happy to answer. Thank you.